Okay, let's dive in. Picture this. You've written a SQL query, maybe something simple, maybe something complex. You hit execute, and it just sits there, grinding.
Oh, yeah.
Or perhaps it was lightning fast yesterday, and today it's suddenly glacial. Sound familiar?
Absolutely. I think every programmer who's worked with databases has hit that wall. It feels like the same query. Maybe the data is mostly the same, but the performance is just completely different. Like the database has a mind of its own sometimes.
Well, today we're doing a deep dive into exactly that mind.
Hmm.
We're unpacking a bunch of material you sent over articles, research, even some notes from a YouTube video I suspect quite a few of you listening might have bumped into.
Right.
We want to explore what happens after you hit execute. We're getting under the hood with database query plans and the incredibly complex component that builds them, the query optimizer.
Think of this as your shortcut to understanding the database's, well, its brain. We'll look at why building this part of a database system is considered one of the most challenging tasks in computer science.
Yep.
Yeah, seriously. Some folks actually say it's harder than rocket science. We'll walk through the whole process, how your simple declarative SQL becomes a concrete series of steps the database engine can actually run.
Because understanding this, seeing this roadmap is just so fundamental if you want to write decent queries, figure out why something's slow, and, feel a bit more in control.
Exactly. It's the key to moving from just guessing and getting frustrated to actually taking informed action.
Okay, so let's start with that roadmap itself. What exactly is a query plan?
At its core, it's the database's step-by-step guide. You write SQL, like select name from users, where it equals 1. That's what you want.
Right, the result.
The query plan is the detailed blueprint for how the database management system, the DBMS, is going to get that data for you. It outlines the exact sequence of operations it plans to perform.
And for you, the programmer listening, understanding this is crucial. It's not just like academic theory.
Not at all. If you don't know how the database intends to run your query, you're basically flying blind when it comes to performance tuning. Slow responses, chewed up CPU or I/O. It often traces back to a less than ideal plan.
It's the diagnostic chart you need to read to figure out why the engine is choking, and the component creating this chart, that's the query optimizer.
That's the one, often called the brain of the DBMS, and honestly, for good reason. When your SQL query lands, the optimizer kicks in. It takes your SQL, looks at the database structure, the schema, the indexes available, and crucially, it uses statistics about the actual data sitting in your tables.
So it knows about the data itself, not just the table structure.
Yes, exactly. With all that info, it starts mapping out potential ways to get the result you asked for.
Okay, so MySQL arrives, this high-level request. How does the optimizer translate that into, the low-level steps?
It's a multi-stage thing. First, the query gets parsed and analyzed. The basic checks, syntax, okay. Tables exist, columns there, that sort of validation.
Standard compiler stuff, basically. It understands the words.
Pretty much. From there, it builds an initial representation of what needs to happen logically. This is usually called a logical plan.
So conceptually,
Mm-hmm.
find data, filter it, maybe join it, that kind of thing.
Exactly. It uses abstract operators describing the core relational algebra. Things like logical scan, I need data from this source, logical filter, I need to apply this condition, logical join, got to combine these two data sets. It's quite high level at this point, maybe even DBMS independent conceptually. It's about the required steps, not the specific algorithm.
But the database needs concrete instructions, right?
Yeah.
How does it get from that abstract what to the specific how?
Right. That's the next big transformation. The optimizer maps that logical plan onto a physical plan. Now, this is the concrete blueprint, and it's specific to your actual database system, PostgreSQL, SQL Server, Oracle, whatever you're using.
Okay, this is where the rubber meets the road.
Precisely. The physical plan uses concrete operators that represent actual algorithms the database knows how to run. So instead of just logical scan, you might see a table scan read the whole table, or hopefully an index seek, use an index to jump right to the needed rows.
Conjoin.
A logical join could become a hash join, or maybe a merge join, or even a nested loop join. There are choices.
Okay. So one logical idea, like join these tables, can have several different physical ways of being done. How does the optimizer pick?
That's the heart of cost-based optimization, or CBO. The optimizer basically estimates the cost of running various alternative physical plans it can think of.
Cost, meaning like money.
No, not dollars. Cost here is an estimate of the resources the database expects to use: CPU time, disk reads and writes, I/O, memory usage, that kind of thing.
And it picks the plan it thinks will have the lowest resource cost.
That's the goal, yeah. Find the most efficient path based on its estimates. And figuring out that cost, well, it depends heavily on several key factors. And understanding these factors is what really helps you when you're trying to tune a query.
Okay, lay 'em on me. What are the big ones?
Probably the single most dominant factor is cardinality. That's the optimizer's estimate of how many rows will flow through each step of the plan.
So how much data each operator has to process?
Exactly. Any operation working on fewer rows is almost always cheaper. If the optimizer thinks a filter will spit out 10 rows instead of, say, 10 million, all the subsequent steps in the plan look way, way cheaper in its calculations.
Okay, so getting that row estimate right is absolutely critical.
Huge. Another massive factor is the access method. How does it actually get the data off the disk in the first place? For really selective queries, like where ed eals 123, an index seek is usually the winner, the cheapest. It pinpoints the data.
Like using the index in the back of a book.
Good analogy. An index scan might read more of the index, but is still better than reading the whole table. A table scan, reading everything start to finish, that's usually the most expensive option, especially for big tables.
And this is why we create indexes, to give the optimizer that fast index seek option.
Precisely. A lot of performance tuning boils down to figuring out why the optimizer chose a table scan when you thought an index seek was possible. Maybe the index wasn't there or wasn't usable for that specific query condition.
Gotcha. And then you mentioned join algorithms.
Yeah.
The big three: nested loop, hash join, merge join. They have different pros and cons.
Big time. The nested loop join is kind of the simplest conceptually. It loops through the first outer table, and for each row, it looks for matches in the second inner table.
Sounds straightforward.
It can be fast if the outer table is really small, and if there's a good index on the join column of the inner table, so those lookups are quick. But if both tables are large and there's no helpful index, it can be absolutely brutal. Performance can degrade really badly, potentially O(n) times m complexity.
Ouch.
Yeah. Its main advantage, though, is it usually doesn't need much memory.
Okay, what about hash join?
Hash join is often the go-to for joining large amounts of data, especially if they aren't sorted and maybe are different sizes. The idea is it builds a hash table in memory using the smaller of the two inputs.
Like a lookup dictionary.
Exactly. And then it reads through the larger input, probing that hash table to find matches. It's generally very efficient.
There's always an if the hash table fits in memory.
Bingo. That's the big but. Hash joins can be very memory hungry. If that hash table gets too big for the available RAM, the database has to start spilling parts of it to disk, maybe to tempted or a similar temporary space.
And disk is slow.
Disk is orders of magnitude slower than RAM. So when a hash join starts spilling, performance just plummets. Seeing hash spills in an execution plan is a major red flag.
Okay, so nested loop can be bad without indexes or on large inputs. Hash join is sensitive to memory. What's the deal with merge join?
Merge join is interesting. It's actually the most efficient join algorithm if both inputs are already sorted on the join columns.
Sorted how?
Like if you're joined on userid and both tables being joined are already physically sorted or have an index that provides that order, then it can just walk through both sorted lists simultaneously, merging the matches. Very fast, very little memory needed for the merge itself.
But what if they're not sorted?
Then the optimizer has to add explicit sort operations to the plan before the merge join. And sorting large amounts of data can be expensive, both in CPU and potentially memory, if the sort itself spills to disk. So the cost of the sort gets added in.
So the optimizer is juggling all these trade-offs: input sizes, sort order, available memory, index availability.
Exactly. Plus other things like data skew are some values way more common than others. The physical organization of data on disk, overall system load. It's a complex calculation.
Right. And you said it relies on statistics for these estimates, especially cardinality, the row counts. Where do those stats come from? How does it know the data distribution?
The main tool here, especially in modern databases, is histograms. These are statistical summaries of the data distribution within a column, instead of assuming values are evenly spread out.
Which they rarely are.
Exactly. A histogram breaks the range of values in a column into buckets and stores how many rows fall into each bucket, roughly.
So it might know that, say, status pending accounts for 90% of the rows, while status complete is only 1%.
Precisely. And that knowledge is absolutely crucial for estimating how selective a filter like where status complete will be. How many rows will likely come out of that step? Without good stats, especially histograms on columns used in filters and joins, the optimizer's cardinality estimates can be wildly inaccurate.
And that's often why you see explain analyze show, like estimated rows, 10 actual rows, 1 million.
That's a classic symptom of stale or missing statistics, yeah.
Right.
The optimizer made a bad guess based on bad info, likely leading to a poor plan choice.
Are there other ways it gets info?
Well, sampling is sometimes used, where it looks at a small subset of the data to guess properties of the whole, though histograms are often more central now. And it definitely uses constraint information. If a column has a unique constraint, the optimizer knows a lookup on that column will return at most one row. Check constraints can tell it about valid data ranges. All useful clues.
Okay, so a query comes in, gets parsed, logical plan, then the CBO uses stats and constraints to estimate costs of different physical operators, access methods like scans or seeks, join algorithms like hash or merge, and picks the cheapest physical plan.
That's the essence of it, yeah.
Let's talk a bit more about those physical operators we might see in the plan output, besides the scans and joins. What else is common?
Right. The plan is usually a tree of these operators passing data up. Besides getting and combining data, you need operators to transform it.
Like applying the where clause.
Exactly. You'll see a filter operator. Its job is simply to apply those predicate conditions. Its cost depends mainly on how many rows are fed into it from the operator below it in the tree, and maybe how complex the filter logic is.
What about sorting for order by?
Yep. There's often a sort operator. And sorting can be quite expensive, particularly if you're sorting a lot of data that doesn't fit neatly into memory. That forces spills to disk again. It is. That's why it's a big win if the optimizer can avoid an explicit sort. For example, if you order by a column that already has an index, it might be able to just read the data in sorted order directly from the index using an index scan. No separate sort step needed.
Nice. And for aggregation, like GPBY.
You'll see aggregate operators, and there are usually different flavors. A stream aggregate is efficient if the input data happens to already be sorted by the grouping keys, similar idea to the merge join. Otherwise, you might see a hash aggregate, which builds a hash table in memory to group the rows.
And that can spill too, presumably.
Just like hash join, yes. If you're grouping millions of unique values, that hash table can get big and potentially spill, hurting performance.
Any other sneaky ones to watch out for?
Maybe spool operators. These are basically temporary storage points within the plan. The optimizer might use a spool to save an intermediate result that it needs to reuse multiple times or sometimes in complex query shapes. They can be fine, but if they're spooling huge amounts of data, especially to disk, they can become a bottleneck. Understanding why the spool is there is important.
So the key theme with all these operators, sort, aggregate, filter, school, is that their cost isn't fixed. It depends entirely on the context.
Absolutely. Context is everything. How much data is flowing in? Does it have useful properties, like being sorted already? How much memory is available? Are there relevant indexes? A sort on 10 rows is trivial. On 10 million, it might dominate the query cost. This context dependency is why just looking at the operator name isn't enough. You need to see the estimates and the surrounding plan.
And this brings us perfectly back to the practical side for everyone listening. When you run explain or explain analyze or whatever your database calls it, you are looking at this physical plan tree.
Yes, you're seeing the optimizer's chosen strategy. And while the output format looks different between, say, PostgreSQL, explain analyze, SQL Server, often graphical plans, Oracle, DBMS XPlan, or MySQL, explain, the core information they convey is very similar.
What should people look for?
You'll see the operators themselves, usually shown in a nested or tree structure. Critically, you'll see estimated versus actual row counts for each step if you run the analyze version that actually executes the query.
That comparison seems vital.
It's probably the single most important diagnostic. If the estimate was 10 rows, but the actual was 10 million, the optimizer was working with bad information, almost guaranteeing a suboptimal plan was chosen. That points you towards fixing statistics, usually.
What else is in the output?
You'll see estimated costs, the numbers the optimizer calculated. Interpreting the absolute values can be tricky and system-specific, but their relative sizes tell you where the optimizer thought the expensive parts would be. You'll see the predicates, the specific filter or join conditions being applied at each step. And with actual plans, you often get resource usage metrics, actual time spent, maybe I/O counts, memory used.
So running explain isn't just some academic exercise. It's literally opening the hood and seeing the engine's blueprint, and with Analyze EE, how closely reality matched that blueprint.
Exactly. It turns the database from a black box into something much more transparent. You can see why it's making the choices it's making.
Now, we've touched on the complexity of estimating costs, choosing algorithms.
Sure.
It
Yeah.
sounds like a huge engineering challenge. You mentioned earlier some sources calling the optimizer harder than rocket science. Why is such a dramatic comparison?
Well, think about it. For any query that's even moderately complex, especially involving several joins, maybe some subqueries, aggregations, the number of possible ways to execute it just explodes.
How many ways are we talking?
It's not just a handful. It can easily be millions, billions, even trillions of potential combinations of access paths, join orders, join algorithms, a truly vast search space.
So actually checking every single one to find the mathematically perfect lowest cost plan is just impossible.
Within the fraction of a second, you expect a query plan to be generated. Absolutely impossible for complex queries. The problem of finding the guaranteed optimal plan is technically NP-complete, which is CS speak for really, really hard, essentially intractable for large problem sizes.
Wow.
So optimizers can't promise the absolute best plan. They have to use clever heuristics, sophisticated search algorithms, and cost models to navigate that enormous search space and find a good enough plan very, very quickly, usually in milliseconds.
So the challenge is finding a very good plan extremely fast, not necessarily a perfect plan eventually.
Exactly. That inherent trade-off, the need for speed versus optimality in this massive search space, is a huge part of why it's considered so difficult. Building a system that does this effectively, efficiently, and reliably is a major feat of engineering.
How did developers even start tackling this? What were the early approaches?
Well, really early, simple databases might have used heuristics-based optimization. Basically, a set of hard-coded rules.
Like, if you see this pattern, do that.
Yeah, things like always push filter conditions down as early as possible, or if joining tables A, B, C, join them in the order they appear in the from clause. Early systems like Ingres and even initial versions of Oracle had simpler rule-driven approaches. They're fast and easy to implement for simple cases, but they break down pretty badly when queries get complex because simple rules can't capture all the nuances.
Less adaptive, more rigid.
Right. The big leap forward was cost-based search, which was really pioneered by IBM's System R project back in the 1970s. That's when systems started systematically generating multiple plan alternatives, estimating their costs using statistics, and picking the cheapest one found.
That sounds much more like what we discussed. And how do modern systems build on that?
Modern optimizers are incredibly sophisticated descendants of that idea. Many use techniques like optimizer generators. Instead of writing tens of thousands of lines of complex C++ code for all the rules and transformations, developers define the rules and operators in a more spiralized, higher-level language or framework.
Making it easier to manage and evolve.
Exactly. It makes the optimizer more extensible and maintainable. And within the cost-based framework, there are different architectural approaches. Some use a stratified approach, maybe apply some heuristics first, then do a cost-based search. Others use a unified search, where everything, including rule-based transformations and cost estimation, happens within a single complex search process. The Cascades framework is a well-known example of this latter approach and is used in systems like SQL Server and others. It's a really deep, active area of database research and development.
It really hammers home that when you just type select from and hit enter, there's this hidden whirlwind of incredibly complex decision-making happening almost instantly.
Absolutely. And that complexity keeps evolving, especially as database architectures themselves change.
Right. How does optimization adapt in things like cloud-native databases or distributed systems? That seems like a whole other layer of complexity.
It definitely is. In cloud-native systems, think Snowflake, BigQuery, Redshift, where storage and compute resources are often physically separate.
Unlike a traditional single server.
Right. The optimizer now has to worry about the cost of moving data between the storage layer and the compute cluster doing the work. Network transfer costs become a factor in the cost model. They also leverage specific features of these architectures. Snowflake uses its knowledge of micropartitions and data clustering to prune partitions that don't contain relevant data. Redshift uses distribution keys and sort keys to try and minimize data shuffling between compute nodes during joins. And the optimizer considers compute elasticity. Maybe using more nodes is faster, but costs more in that sense.
So the cost model expands beyond just local CPU, I/O, memory, to include network and potentially resource provisioning.
Exactly. And then In truly distributed databases like CockroachDB or TDB, where your data might be sharded across dozens or hundreds of nodes, the absolute primary challenge for the optimizer is minimizing network communication. Moving data between nodes is usually the most expensive operation.
Makes sense.
So their optimizers focus heavily on pushing processing down to the nodes that actually hold the relevant data fragments, applying filters locally before sending data across the network. Choosing distributed join strategies designed to minimize data movement, maybe broadcasting a small table to all nodes that need it, or repartitioning data dynamically so that rows that need to be joined end up on the same node.
Like CockroachDB's distributed SQL execution engine trying to keep work local.
Spot on. The fundamental ideas of cost-based optimization still apply, but the cost model gets much more complex, and the set of available physical operators expands significantly to include these distributed operations.
Wow. Okay, so we've really journeyed quite far today from seeing that simple SQL query land to understanding the logical what, the physical how represented in the query plan. We've explored the optimizer's brain, how it uses cost estimates based on statistics, the different algorithms it chooses from, and even why building this whole thing is apparently harder than rocket science.
Yeah, hopefully peeling back those layers helps demystify what's happening when you hit execute. The goal is that now, when you look at explain output, you have a better framework for understanding it. You can spot those telltale signs like bad cardinality estimates and have a better idea of how to write queries that give the optimizer a good chance of finding an efficient plan right from the start.
Moving beyond just hoping for the best.
Exactly. You gain insight into the process.
It really does shift the interaction from feeling like you're dealing with a mysterious black box to having a more informed conversation with the database system.
Which kind of leaves us with a final thought for you to ponder. We've established that Query Optimizer is this incredible piece of engineering, making super complex choices based on statistical estimates and heuristics, all under intense time pressure. It's brilliant, yes, but also inherently imperfect because of those estimates and the sheer scale of the problem. So how does knowing about this inherent uncertainty, this reliance on good enough, influence how you should approach designing your database schemas, writing your queries, and deciding how much trust to place in the plan the optimizer gives you? Is the plan it chooses automatically always sufficient? Or do you sometimes need to dig deeper, understand its logic, and maybe guide it towards an even better solution for your specific needs?
Definitely something to think about the next time you're faced with a query that isn't quite behaving as expected.
Mm.
Now, hopefully with a much clearer picture of what might be going on under the surface,